Thank you very much, Dr. Mayboom, for this kind introduction. Indeed, I'm happy to introduce the Quantra system to you, a system developed and manufactured and marketed by HemoSonics, a new viscoelastic device for assessing coagulopathy. As Dr. Mayboom mentioned, assessing coagulopathy is important because that will guide transfusion management. Before going into the details, I'd like to do a little poll with you. So based on your experience and your perception, I'd like to ask the audience, what do you think is the biggest challenge to using whole blood viscoelastic testing in an effective manner that provides the most benefit to patients? And these are the possible answers. Is it timely availability of results? Is it education, interpretation of results? Standardization of algorithms and compliance to these algorithms, or quality control for reliability of results? So please start the poll. Okay, that's interesting. Timely availability of results and education interpretation of results are the top sort of barriers that you see. Okay, it's interesting to see the perceptions on or experiences on introducing point of care viscoelastic testing in a patient blood management program. As mentioned before, optimizing coagulopathy is one of the key elements of patient blood management, and that is really enabled by a goal-directed therapy using point of care viscoelastic testing. And that's also recognized in many professional guidelines, as you can see in this slide. And the Quantra system is one of those point of care viscoelastic testing. And in contrast to other systems available in the market, this is based on a novel technology called sear sonoriometry, and I'll discuss the details in the next slides. It's really designed to deliver fast results in an easy to interpret way at the point of care. So simplified interpretation operation is the key element of this system. The technology is called SEER, which stands for Sonic Estimation of Elasticity via Resonance, and it's an ultrasound-based technology. We basically use a high-energy ultrasound pulse in the megahertz frequency range, similarly to what is used to do imaging tests on patients, for example. This high-energy ultrasound pulse creates a shear wave, and the blood sample starts to resonate, starts to move. The blood cells start to be displaced from their original position. And at the same time, coagulation is activated by either kaolin or tissue factor, activators of either the intrinsic or the extrinsic path. The coagulation is starting, fibrin formation is starting, the clot starts to be formed, which gives an increase over time in the clot elasticity or the shear modulus. The shear modulus is the physical parameter that's being measured. So during the coagulation process, the displacement of the cells is changing and is diminishing over time. And the shear modulus is calculated from this displacement. And then over time, you see this curve. You see here that an increase in the shear modulus over time. The advantage is that there are no mechanical interactions with the blood sample, so no mechanical clot disruption is possible. And it's also very sensitive to soft clots and not sensitive to environmental vibrations. This gives you excellent precision. So how do we display the results and how do we interpret the results? Basically, we can derive two types of parameters from this curve, where you have a display of the change in shear modulus, the viscoelastic properties over time. So this point here, where the shear modulus starts to increase, that's the clot time. And that's representing the Drummond generation. And then 7 minutes after the start of clot formation, we measure the clot stiffness from the curve. There is no need to wait until you reach full clot firmness. The clot stiffness that we measure at 7 minutes is very predictive of the total clot stiffness that is measured later. But it gives you a much earlier result, and that's also important in critical care management. So the clot times that are measured on the Quantra system are from the initiation of the clotting pathway by kaolin. So this is an intrinsic clotting time, which is being measured both in the absence and the presence of heparinase. And also the ratio between the two clot times is calculated. So in this example, you see a normal CTH and a prolonged CT clot time with a very high ratio between the two of 2.9. So this is an example of a patient with residual heparin. The bottom line of the display gives you the clot stiffness values. So we measure total clot stiffness, which in this example is normal, 24.1 hectopascal. And we can also measure the fibrinogen contribution to clot stiffness by blocking the influence of the platelets by adding a platelet inhibitor called abciximab, which is a blocker of the fibrinogen receptor. And in this example, that gives you a value of 2. And then if you subtract the FCS value from the total value, you get your platelet contribution to clot stiffness, 22.1 in this example. In this display, we have 4 measured parameters and we have 2 calculated parameters. The CTR, the ratio between 2 clot types, is calculated. Also, the PCS value is calculated. On a different cartridge with a different set of reagents, it's also possible to measure fibrinolysis. And to measure fibrinolysis, we need a prolonged measurement time because it happens after you reach the peak. And then we measure the decline in clot stiffness in the presence or absence of tranexamic acid, which is an inhibitor of plasmin, the active fibrinolytic enzyme. So if there is no fibrinolysis, which you see in this panel here, the 2 curves in the presence or absence of tranexamic acid are perfectly parallel. Whereas in this example, where there is indeed hyperfibrinolysis, there is a much more steeper decline in the clot stiffness in the absence of tranexamic acid. And from the difference in the slopes, a CSL parameter is calculated, which stands for clot stability to lysis. So in absence of lysis, it will be 100%, and there is significant hyperfibrinolysis, then it will be less than 93%. And in this example, you see a CSL value of 10%, which is really a very, very hyperfibrinolytic sample. In a nutshell, by looking at the display, which is in these dials, you can immediately see where you are on the hemostatic balance, what is happening in the patient. For the clot times, for example, you can immediately see whether it's normal, whether you have a prolonged clotting time, so a slower trauma generation, which could be negative of factor deficiency or the presence of heparin, or whether the sample is more quickly clotting, which could be an indication of hypercoagulability. For clot stiffness, it's the other way around. When the clot stiffness is below the normal range, which is indicated by the green bar, you have a softer clot. So that's a sign of hypocoagulability or bleeding, for example. When there is a stiffer clot, a hypercoagulable clot, which could be associated with thrombotic risk, as we see in COVID-19, for example, you get a very high clot stiffness value, which is above the normal range. And for fibrinolysis, again, you can immediately see what's happening if you have a normal resistance to fibrinolysis or a faster breakdown, hypofibrinolysis. So ease of interpretation and reading is one of the key benefits of the Quantra system. But it's also possible, like other viscoelastic testing, to look at the curves, and you can also view them in real time. And if you're measuring the same patient multiple times during an operation, for example, it's also possible to look for trends over time in that patient for the various parameters. There are 2 cartridges available. One is named Q+, and the other is named QSTAT. The Q+ cartridge is the one that has the possibility to look for residual heparin, so comparing the clot times in presence or absence of heparinase, which is particularly designed for use in cardiovascular surgery and major orthopedic surgery. The other cartridge is designed to measure the fibrinolysis pathway, and that is very applicable for use in trauma, liver transplantation, or obstetric procedures, for example. So this is a display of the cartridge, how it looks like. So it's a plastic device that contains the reagents in lyophilized form. It is inserted into the system. A blood tube, a citrated blood tube, is added, which contains 3 ml of whole blood citrated blood. The blood is sucked into the system, is pre-warmed, mixed with the reagent, and then automatically transferred into the measurement chambers here where the ultrasound detection is taking place. That operation is very simple, it's very fast, and within 60 seconds, everything goes. The Q+ has 6 output parameters I discussed with you previously, as you see displayed here, in which CTR and PCS are calculated, and the QSTAT has 5 parameters on the display, including the clot stability to lysis parameter. And results on the Q+ are typically available in less than 50 minutes. If you're interested in lysis, there is a longer measuring time, but still you get the results in less than 60 minutes. This shows you the workflow. It's very easy. So both the cartridge as well as the sample are being scanned. So you push in the cartridge, then you scan the sample and you push down the sample. and then you press the start button and you're ready to go and get the results in less than 15 minutes. Now let's look at some data, some publications on the clinical performance of this device. This is a study published about a year ago in anesthesia, a study done in the UK in cardiac surgery, where the Quantra Q+ parameters were measured at 3 different time points: baseline, before operation, on bypass, and after protamine reversal. And what you see here is that the various Quantra parameters are really following what you also see with standard lab tests. So the APT, the clot times, as you can expect, are prolonged due to the procedure. Platelets are going down due to the procedure, and also fibrinogen levels are going down. And similarly, you see a prolongation of the CT and CTH with the procedure. The clot stiffness is going down, both due to platelets as well as due to fibrinogen. So there is a very nice correlation with existing standard lab tests. This is a larger study where we looked at correlation with the Klaus fibrinogen, the correlation of the FCS parameter on the Quantra with the Klaus fibrinogen method, the standard lab method. This was done in a large multi-center US study where we had more than 800 data points from patients undergoing either cardiovascular or major orthopedic surgery. You see a very nice correlation, and Pearson R value of 0.78. But what is also done in this study is that by means of an ROC analysis, the predictive power was analyzed for low levels of fibrinogen, either 120, 150, or less than 200 milligrams per deciliter. And the area under the curve, as you can see here, are quite good, are well around 90%. So a very good predictive power for low fibrinogens. And from this rock plot, you can also assess equivalent threshold values for these low fibrinogen levels, as you see here in this table, with very high sensitivity and specificity for predicting those low levels of fibrinogen. Similarly, from the same data set, also the association and correlation with platelet count was analyzed. And also here you see a very good correlation of the PCS value, the calculated value, by subtracting the FCS from CS with platelet counts. And again, with ROC analysis, you see a very good predictive power for low platelet counts. And again, from these rock plots, equivalent threshold values were assessed for the various low levels of platelet count with very good sensitivity and specificity. Going back to the platelet contribution to clot stiffness, what we call PCS, as I showed you in the previous slide, this had a very good correlation with platelet count. But an important aspect is that what we call platelet contribution to clot stiffness is not only influenced by the number of platelets, but also by their functionality. Platelets play a very important role in clot formation, not only by aggregating and forming the clots, but also by providing a catalytic surface for thrombin generation. And the whole process of thrombin generation and fibrin formation is taking place on the surface of activated platelets. So you do not only need enough platelets, but they also need to be functionally active. And that's actually shown in this study, where the investigators showed that the PCS value not only correlated quite well with platelet count, but also with platelet function as measured by the multiplate ADP. And by multivariable regression analysis, they could see that the PCS value could be explained both by platelet count as well as by ADP-dependent platelet function. Besides studies showing the association and the correlation with standard lab tests, several studies have also been done to show the correlation with existing viscoelastic testing method. And this is a study done in the US, a multi-center study showing the correlation with the Rotem delta. And as you can see, the equivalent parameters on the Rotem delta correlated quite well with the Quantra parameters, with R values around from 0.84 to 0.89. However, although the results can be expressed in the same units, seconds with respect to clot time, or Pascal or hectopascal when it comes to clot elasticity, even when expressed on the same unit scale, the results do not agree. They correlate very well, but they are different. So the Quantra CT is shorter than an INTEM or a HEPTEM CT, for example. If you look at the curve here, 200 seconds on the Rotem will give you 150 seconds on the Quantra. So the Quantra clotting times are shorter, and the clot stiffness values on Quantra are higher. The blue points here show you the correlation of the amplitude in millimeters with the clot stiffness values on the Quantra, and there is a non-linear association, but it's possible to convert the millimeter values, the amplitude values in millimeters, into a clot stiffness value in Pascal. There is a formula that allows you to do that. Then you get a very nice straight relationship, which you see here with the orange dots. But even then, if you compare the results, for example, here we have 1000 or 10 hectopascals on X10, that will then be equivalent to 25 hectopascals on the Quantra. So the Quantra gives you about 2.5-fold higher value than on the Rotem. Basically, this means that every system needs its own device-specific threshold values to guide transfusion. Similarly, in a comparative study with the TEG, we also saw very high levels of correlation in terms of the R values, but again with shorter clot times on the Quantra and higher clot stiffness values on the Quantra. Finally, study was also done on the new cartridge, the QSTAT cartridge, that also allows you to measure fibrinolysis in trauma patients. This was a multi-center study done in the US in level 1 trauma centers, where 56 adult trauma patients were tested with a median revised trauma score of 12. So this is a relatively mild severity of illness. Again, as in the previous studies, we saw very good correlations with the Rotem parameters, R values of around 0.8. And also the CSL parameter, which is assessing the fibrinolysis on the Quantra, is showing a very high level of correlation with a similar parameter on the Rotem, the X10 maximum lysis parameter, an R value of 0.95. In a concordance analysis, the concordance was almost 97%. As you can see in this table, there were 5 patients where both devices scored the patients as being hyperfibrinolytic. So the CSL value was less than 93%, and the maximum lysis value of the Rotem was more than 50%. 51 patients scored the patients as having no fibrinolysis, and there were 2 discordant values, where the Quantra indicated that these were hyperfibrinolytic, but that was not the case on the Rotem. So these results also indicate that the Quantra QSTAT system can be a very useful aid to monitor coagulation of fibrinolysis in the trauma population. I will also share you some results that were obtained in patients with COVID-19, and it's known from the literature and many reports showing that these patients can be very prothrombotic. There is a high incidence of thrombotic events in these patients. They show a very hypercoagulable profile with very high D-dimer levels, very high fibrinogen levels, and we also see that in the Quantra profile. So on admission, in this study done in Italy, we see unchanged clot time. The clot times values are not really changed with respect to normal, but what we see is very high clot stiffness values. Total clot stiffness, as well as the platelet contribution and the fibrinogen contribution to clot stiffness, are way above the upper limit of normal. And interestingly, when these patients were treated aggressively with antithrombotic therapy, over a period of about 2 weeks, all the clot stiffness values came down into the normal range. A French study also showed very similar, very high clot stiffness values in patients with COVID-19 and acute respiratory distress. Whereas in patients with acute respiratory distress, but without COVID-19, did not show these very highly elevated clot stiffness values. This is just a summary slide that gives you a listing of the literature that is currently available on the Quantra device, and I reviewed some of the key papers with you in my presentation. So this is where I stop, and please, if you have any questions, don't hesitate to put them on the chat, and I'm happy to answer them later.